So today we're going to introduce nuclear chemistry. So this intro is going to be about radioactivity and table O and things like that, and we'll eventually get to transmutations, but let's start. So sometimes in chemistry, you have atoms that are unstable. Now what atoms do when they're unstable is they give off radiation. Radiation can be an energy or a particle that comes out of the nucleus of an atom. When an atom gives off radiation, it's called a radioactive decay. So the process of giving off radiation is called a radioactive decay. And it's the act of ejecting energy or particles from the nucleus. The reason it does this is to become stable. Now, sometimes atoms don't become stable after a single radioactive decay. They have to do a series of them, and then we end up with what's called a series of decays, or a decay series. So that does happen too, but that's the eventual goal, is to be stable so you don't have to give off radiation anymore. All elements larger than atomic number 82 are radioactive, and for the ones that are smaller than 82, they can be radioactive depending on the isotope. And what ultimately determines if they're radioactive or not is the proton to neutron ratio. So the magic ratio is 1:1. So if you have 1p for every 1n, you are typically stable. So if we look at these two carbons, we've got carbon 12 and carbon 14. Carbon 12 has 6 protons, 6 neutrons. That reduces to 1:1, therefore it's stable, therefore it does not give off radiation. Carbon 14 is 6 protons to 8 neutrons. Now granted, you could reduce that to 3 to 4, but that doesn't matter. If it's not 1:1, that's what this line through the equal sign means, it's not equal. If it's not 1:1, therefore it's unstable and it does give off radiation. Now I will say that the 1:1 works most of the time with smaller atoms. So atoms that are typically smaller than calcium, so element 20 or smaller. And when you start getting above element 20, they tend to need more neutrons than the 1:1 ratio. They'll creep all the way up to like 1.5 to 1 when you get to elements that are 90 and higher. They might be 1.5 to 1. So a pure 1:1 works for the elements that are smaller than atomic number 20. When they get bigger than 20, they start to need a little bit more sometimes. Sometimes they're 1:1, but in general they tend to start needing more. Now, this is what your table O looks like. So you have this on the back of your reference table. The only difference is you don't have the charge column and you don't have the what is it column. So these two columns you're going to add in. So you could do this in two ways. You could write this in your notes, or you could go directly to your reference table and go to table O. And add it right here. So you could also just do this and just kind of put 2 additional columns in there and fill it in that way. That's totally acceptable too. So I don't care where you put it. This might actually be better as long as you don't lose your reference table. And that's pretty much what you do. So these are the types of radiation that we have to worry about. We have alpha particles. An alpha particle is its symbol is He42, or this weird looking fish thing. I kind of draw it, I overdraw it, and I draw it like that. Sometimes it gets underdrawn and it looks more like an A. It depends on the font you use, but that's a Greek letter alpha. The numbers are the same. And so what is it? It is a helium nucleus with no electrons. So it's a helium nucleus that gets ejected out of the neutron, basically a cluster. We say it's a helium nucleus, and it is, but it's a better way to think of it is just 2 protons, 2 neutrons that are stuck together that get shot out of the nucleus at high speed, and that's effectively what an alpha is. It is in fact a helium, I mean, because the 2 protons makes it helium, but you could think of it either way. I don't care. Charge is +2. Beta, what is it? Well, you could use 0 - 1e or 0 - 1 with this weird looking B, which is a Greek letter beta. It's an electron. It's an electron that gets shot out of the nucleus. Yes, you heard that right. I can explain more of that later on. Charge is -1. Gamma, it looks like a Y, but it's actually a Greek letter gamma. I tend to overdraw it like this so that it's a little bit more obvious. And it's 0, 0. And what is it? Well, it's a form of light. So it's a high energy X-ray. We can't see it with our eyes. It will go straight through you. It has no mass, no charge, and it's typically accompanied by alpha and beta. So you do get a gamma alone, but a lot of times you get alpha and gamma and then beta and gamma. Gamma kind of like comes with other types of radiation very often. And then we've got neutron decay. It's a neutron, charge 0. That's pretty easy. Symbol lowercase n. Proton decay, it can be used as a lowercase p, which is proton, or an H for hydrogen, because if you have one proton, you are in fact hydrogen. So either symbol works. Charge is +1. It's a proton being shot out of the nucleus. And a positron decay. It sounds like electron, but it has the word posi in it, right? Because electron, I guess you could say it also sounds like neutron, but it is actually a positive electron. So that is antimatter. So that is basically an antiparticle to an electron. It's an electron with a positive charge. When an electron and a positron touch each other, they do destroy each other. There are some medical technologies that actually utilize that, but that's pretty much what it is. And it does, in fact, get emitted. It is fairly common, at least in our chemistry class, you'll hear about positrons a decent amount. And that's it for table O. Those are the types of radiation you have to worry about. There are other types, but we're not going to get into them. And now let's look at transmutations. So this is the nuclear transmutations that you have to worry about. So a nuclear transmutation, what is it? Well, it's a radioactive decay, but it's more specific than that. It's a radioactive decay that causes one element to turn into a different element. It's doing that to become stable. Again, that's the ultimate goal. It's based on the law of conservation of mass, charge, and energy. So there's 3 laws right there. We just kind of lump them together because they all say the same thing. Conservation of mass means mass can't be destroyed, meaning you can change its form, you can move it around from one element to another, but you can't actually destroy it. Same goes for charge and same goes for energy. Okay, one thing to keep in mind, the way we're going to do emission and capture is you actually figure out if something is emission or capture, which are types of transmutations, based on the arrow in the reaction. If the particle that we're talking about is on the left of the arrow, it's called a capture. If the particle we're talking about is on the right of the arrow, it's called a decay. And I'll explain that a little bit more, but let's go over emissions and captures. So an emission is what we would call a natural radioactive decay. So the thing is, when you think of emissions, they are natural decays, whereas captures are going to be artificial, which means that happened in a lab and it was done by a scientist. It didn't happen in nature, okay? So let's look at alpha emission, right? So that's actually when a nucleus shoots out an alpha particle. So before we do that, we're going to need to go to the periodic table because we need our atomic numbers. So Fr has the atomic number 87, all right? And helium is 42, so we have to write those in. And here's what happens. If an Fr were to lose a helium from its nucleus, so it just shot it out, right? Well, then its weight would go down. It would go down by 4 because that's how much the helium weighed, and its number of protons would go down by 2 because that's how many protons the helium had. So if we think about our arrow as the universal equal sign, everything on the left has to add up to equal everything on the right. Now, granted, we treat the top numbers and the bottom numbers different, but it's still, the law of conservation of matter still works. So in other words, I have 220 AMUs, or atomic mass units, on the left. My right side is going to have to add up to equal 220. So if 4 of them are here, then the blank is going to make up the other 216. That's not enough to tell me the symbol of the element, but it will tell me the mass. Now I do the same for the bottom. 87 on the left, I'm going to have 87 on the right. 2 of them come from the helium, so the remaining 85 have to come from the new element that's formed, which is At. So this is called a transmutation because when the francium atom ejects the helium, or the alpha, it is now turning into At. Reason being is because its number of protons went from 87 to 85, so by definition, its element changed. Let's do a beta decay, or a beta emission, right? These are also, well, we'll get into that later, but so for the beta emission, we have a carbon, it's 6. The beta numbers are 0, -1. The arrow is always your equal sign. So this one's tricky because we have a negative involved, but as long as you pay attention to that, it's not a big deal. I've got 14 on the left. I'm going to need 14 on the right. 0 comes from the beta, so therefore the remaining 14 all have to come from the new element. And I have 6 on the left. I'm going to need 6 on the right. -1 is coming from the beta, so that means the new element has to account for 7 of them, because 7 plus -1 is 6. That makes the right side equal to 6. And so again, when carbon does a beta decay or a beta emission, it turns into nitrogen as a result. Last one, neon, atomic number 10, and positron, +1 at the bottom. So the top number is going to be 19. That's just like the other one. And the bottom number is going to be 9 now, because it's 9 plus 1 to equal 10, and then 10 on the left. And element 9 is F, or fluorine. All right, so those are the emissions. These are also called radioactive decays, right? Or natural radioactive decays. One way of knowing that they are natural radioactive decays is going to be natural decays only have one reactant. The reactant is the thing on the left. So if you look, they only have one thing on the left. Okay, and that's how it works. Whereas the artificial always have 2 things on the lefts. I'll explain it in another way once we finish this, but let's do the captures, and then we'll get started on the explanations and wrapping it all up. So this is 87 again. That's 2. But all I did is move the arrow. So these are saying 2 different things. In alpha emission, the alpha is on the right side of the arrow, so therefore it's leaving or coming out of the nucleus. That's what this is for. And in an alpha decay, or sorry, in an alpha capture, the alpha is on the left side of the arrow, therefore it's going into the nucleus. So that's really the difference. In the emission, the nucleus is being shot out of the FR, or the francium atom, and in the capture, the nucleus, the helium is going into the francium atom, making it bigger and heavier. That's the difference between capture and emission. So for this one, since the arrow is over here now, 220 plus 4 is 224, and there's only one thing on the right, so it has to be 224 to make it equal. 87 and 2 is 89, so that means the right side also has to be 89. And element 89 is AC. So it's still a transmutation because it's turning into a different element. It's just, instead of leaving the nucleus, the helium is going into the nucleus. This one's going to be the same as well. 6 minus 1. I get 14 on top because 14 plus 0 is 14, and I need 14 on the right. And then this 6 plus -1 is 5, so I'm going to need 5 on the right, and that is B. And then the last one, I have 19 and 0 on the left, so I'm going to need to have a total of 19 on the right, since it's all in one thing, or all in one element. It gets the whole 19. And I have 11 on the left for the bottom numbers, so I'm going to need 11 on the right, which is sodium, Na. And then this would be an artificial decay, and the reason is there's always more than one reactant. So the reactants are the things on the left, there's always more than one of them, and the products are the things on the right. So to figure out if it's artificial or natural, we always look at the reactants. All right, and that's pretty much it. One way of explaining artificial and natural radioactive decays, the element decays on its own. There's nothing helping it. And so that's why there's always one product, or I'm sorry, one reactant in the reaction, because it's literally just enough time passes, this thing's unstable, so it gives off its radiation, and that's it. For captures, you have to have the atom, and then you have the atom that's your target atom, and then you have the thing you're going to shoot into your target atom. And things in nature don't shoot at other atoms. Like, there's no natural version of an atomic gun in nature, right? There's no guns in nature at all. And so in nature, this doesn't really happen. You're not going to have a alpha particle randomly speed up to almost the speed of light and then get shot inside of a francium atom to make the francium atom heavier. There's no contraption in nature that's ever going to make that happen, which is why these are always artificial, because they have to be done in a lab. And that's actually how they do it. They usually take your francium atom and they leave it still, and then they basically make the atomic version of a gun, and they shoot that alpha particle at very high speeds into that francium atom, and then they hope that it sticks and it doesn't break the francium atom up and make it, break into a million pieces. But that's natural versus artificial, and that concludes our intro to nuclear chemistry.